Hi guys, so today I'm going to be doing this question from step 3, 2015, and yeah, so it's obviously integration question, and it's quite nice in the way that it links the steps together, so you get quite a lot of good clues from that. Okay, so let's get right into it. So we have the integral between 0 and infinity of 1 over 1 plus u squared to the n du, and this can be equal to I of n. Okay, and we need to show that I of n minus I of n plus 1 is 1 over 2n I of n. So I think that's what we're looking for. Yeah, okay, so we have integral between infinity and 0, okay, of 1 over 1 plus u squared to n minus 1 plus u squared to n plus 1. That looks like a 2. Okay, so now we want to be able to subtract this, so we want the same denominator for each. So this would be 1 plus u squared minus 1 over 1 plus u squared to n plus 1 du, okay, which we know will simplify to u squared over 1 plus u squared du, okay, and it's between 0 and infinity. Okay, so I of n minus I of n plus 1. So when we're solving an integral in this particular type of way, you know, we haven't already found out what this is equal to, so it means we're probably going to have to use by parts, okay? And, sorry, n plus 1. What we can notice from this parts is if we make u equal to u equal to u over 1 plus u squared to n plus 1, it gives us a nice solution. So we can have v being equal to 1 over 2n, and this is negative, I believe, 1 plus u squared to the n, okay, and then u prime is just going to be equal to 1. Okay, so I of n minus I of n plus 1 is the integral. Well, so we have u minus u over 2n 1 plus u squared to the n, and this can be between, we'll do limit t tends to infinity between t and 0, okay, and if we look at this, obviously the 0 will be a 0. With t, we've got greater order on our denominator, so this is actually just going to be 0. For our integration part of our parts, we want to do minus u prime times v, so this would turn into a plus, okay, so we have plus 1 over 2n, because n is constant, times the integral between 0 and infinity of 1 over 1 plus u squared to the n du, which is I of n. So it gives us I of n minus I of n plus 1 is going to be equal to 1 over 2n of I of n, which is what we're looking for. Okay, so for this next part, we want to deduce this. Okay, so first of all, we want to make I of n the subject, because that's the thing that we're trying to solve. So I of n plus 1 is going to be equal to I of n minus 1 over 2n of I of n. Okay, so that's gonna be equal to, if we times this by 2n, we'll have 2n minus 1 over 2n of I of n. Okay, so what we want to look at here is, if we have this would mean that I of n, okay, it's going to be equal to 2, okay, and this will be n minus 1, okay, over 2 n minus 1 times I to the n minus 1, okay, and if we look, this will follow a pattern, okay, so I to the n minus 1 is going to be equal to 2 to the n minus 1 over 2 to the n times 2 to the n minus 3 over 2n minus 2 times 2n minus 5 over 2n minus 4, and then eventually we've got to look for our last term. Okay, so this one is 2 times n minus 1. Okay, we know that essentially we're going to want to go down to I of 1, okay, because it'll give us a nice solution of a half. So half times I of 1. Okay, so I think first it could be pretty easy to just solve I of 1, okay, which is the integral between 0 and infinity of 1 over 1 plus u squared du, which is the standard result of arctan u, which we will evaluate with limit as t tends to between t and 0. Okay, and then this, sorry, that's infinity, but anyway, this will give us pi over 2. Okay, so I of n minus 1 is 2n minus 1 over 2n times 2n minus 3 over 2n minus 2 times pi over 2. And then that's also times a half. Okay, so if we ignore the pi over 2 for now, we've got, okay, so this bit here, what I think we need to look at is it in relation to what we're given here, because deriving this without knowing it beforehand would be way more difficult. Okay, so we've got 2n factorial times pi, and then we have 2 to the 2n plus 1 times n factorial squared. So 2n plus 1 times n factorial squared. Okay, if we divide by pi over 2, we know that from the other stuff we can have 2n factorial over 2 to 2n times n factorial squared. Okay, and then we need to basically compare this, and the first thing we want to look for is this 2n factorial and how we can make this 2n factorial. And what you see is it skips a term, so we would want 2n, we would want 2n minus 2, and you know, going further, you notice that what we're missing is the denominator. So if we square the denominator, this will give us 2n factorial. Okay, and I'll put that in brackets. If we look at the denominator now, okay, what was that equal to? Okay, if you were to look at n factorial, okay, we basically can see this being, okay, 2 times n, and then we have 2 times n minus 1, okay? So that is 2 to the n times n factorial, okay? But we're going to square it, so we're going to have 2 to 2n times n factorial squared times pi over 2. That's going to give us our result. So pi 2n factorial over 2 2n plus 1 times n factorial squared. Very nice. Okay, part 2 now. So we're given a new integral of j equal to the integral between infinity and 0 of our function f of x minus x to the minus 1 squared dx. Okay, so we want to find j here, and we see that we've got this and it's multiplied by x minus 2, okay? And what I'm thinking is, how do I get that x minus 2? And instantly we're going to use substitution, and I know that if we have x minus 1 and we differentiate that, okay, we get minus x to minus 2, and that's going to be, yeah, okay, that's it. Okay, so we're going to do u equals this, du is equal to this, dx, alright. So now what we're going to want to do is sub all of this in, okay? So our dx is going to be du over minus x minus 2, okay? Which, okay, if we look at minus x to minus 2, we see that u squared is x to minus 1, or x to minus 2. So this is divided by u squared, or minus u squared. Okay, so I'm going to look at the limits in a second, but we're going to have f. So if we look at this, we have minus u to the minus 2, f of, okay, x, okay, so we have that this is going to be minus u, obviously, but then x is going to be, if we look at u equals 1 over x, x equals 1 over u, okay, so this is u to the minus 1 minus u squared, and now it's to u. Okay, limits. Essentially what we're going to see from these, which is quite nice, is essentially it's the inverse of the other limit. So as u would tend to 0, x would tend to infinity, and vice versa. So this is going to be just switched, and what we notice here is the minus can cancel these limits, okay? So we have this f of u to the minus 1 minus u squared du, which is now looking very similar to this here. However, we've got a slight difference here. However, what we can notice from this is that we're squaring, so it's going to give us the same result either way. And as well as this, we've got x here, we've got u here. X and u are just variables. It doesn't matter what we call them, so we can call this x to minus 2, f of u to minus 1 minus u squared du, okay, or I forgot to do my x's, or even, there we go, okay, so that fulfills that form. So this can be equal to j. For this next part, there's one thing that instantly stands out, which is the half, okay? And from that, what I'm thinking of is we've got two solutions for j. So when I was first doing this question, I was like, okay, we add them together. And that gives us that 2j is going to be equal to the integral between 0 and infinity, and then we can just add these two. Okay, so we have x minus 2, f of x minus 1 squared dx, plus f of x minus 1 squared. Okay, and I'll put the dx at the end. And then we can notice here that this simplifies, and then this is 1 plus x to minus 2 because we have the same function here, and f of x to minus 1 squared dx. Okay, so now we want this final form. So u squared shows us that we're going to substitute. The fact that the u is squared gives me a hint to just sub this in, okay? The other way we know that this is the right sub is when we differentiate this, we get 1 plus x minus 2, which is this. So the question gives you quite like a lot of help with knowing which substitution to make, which is pretty nice. Okay, so j is going to be equal to, or I'll make this up first, okay? Okay, this will go back, or whatever. I've just got to put in my 0 to infinity, okay? So we want to sub this. So u equals x minus 1. We don't want to square it. Okay. Du equals 1 minus plus x minus 2 dx. Okay. So we know that these will cancel, yeah. Okay. Now we've got to look at is our limits, yeah. So infinity, when x equals to infinity, this is infinity minus 0, so it's infinity. And at 0, okay, we have 0 minus, this will tend to infinity. So we have minus infinity, okay? So we're going to have that j is equal to a half the integral between infinity and minus infinity of a function, which is now u squared, okay, du. And so what we need to notice here is because it's a u squared, we've got an even function, okay? Due to that, we can cancel out this half and cancel out that minus infinity to make it 0, because when it's negative and positive, you're going to get the same result. So that's very nice, and that gives us the solution. Now I've got this last part, okay? So when we're knowing here already that we're going to want to use those parts, they're not going to make us do that for nothing. So that's useful, and we just got to see how. Okay, so x4 minus x squared, and that's a plus 1 dx, okay. So instantly, yeah, what I'm going to want to do, this should be to the n, is split my powers, because it's not very nice to have them like that, and you got to see if there's some cancellation that could happen. So we've got x to the 2n times, okay, x to minus 2 dx, and then it's over x4 minus x squared plus 1 to the n. Okay, so because this is in terms of n, what we can do actually is divide by x to the 2n, which simplifies this nicely into x to minus 2 over x squared minus 1 even plus x to minus 2 dx. Okay, so this is a lot nicer now. And what we're going to see here is it's similar to what we had earlier. So earlier I think we had x minus 1 squared, and that was our function. That's what we had in our function even. Okay, so we're going to see what happens when we square it, and it's going to give us, okay, x squared, okay, minus 2, and then plus x to minus 2, which is very similar to this. So this is just going to be plus 1, okay, and then that's going to be equal to this. So we have the integral between infinity and 0 of x to the minus 2 of, okay, x minus 1 squared minus 1 dx. Okay, and now it's very nice, okay? Because, again, we can look at this and we've got x minus 2 here, and we know that gives us f of u squared, which is pretty much what we have, except it's a u squared plus 1, okay? Sorry, I just took away that n and all of that. Okay, so now we know that this is simply gonna be f of u squared. Okay, so we've got the integral between infinity and 0, okay? And we're gonna have 1 over u squared plus 1, okay? And this can be du. We're gonna have this to the power of n as well. Okay, so now we need to evaluate this, okay? This is I of n, and we saw I of n earlier in this part here, okay? We found that I of n plus 1, okay? So I of n plus 1 is equal to, if I can remember, I think we had 2n factorial times pi over n factorial squared times 2 to 2n plus 1. Okay, I'm just going to check that that's right. Yeah, okay. So, this is quite nice now, because this is the same as this, just as n minus 1. So we need to plug n minus 1 in here. So we have 2 n minus 1 factorial times pi over, okay, n minus 1 factorial squared times 2, and that's just going to be n minus 1. So 2n minus 2 factorial times pi over, I think that's right, and then that'll be over n minus 1 factorial times 2 to 2n minus 1, which I think is the correct final form. So yeah, thank you for watching, and I hope you learned something from that, and especially within, like, not just this question in particular, but approaching a step question in general. And you know, this gave you so many hints on where to go with the question that it's actually not as heavy on problem solving as other step questions, even though, like, immediately this looked pretty scary to me.